Okay, so what we're going to go over now is how you can figure out which normal modes, once you have them, are stretches and which ones are bends. And so first what you're going to do is you're going to actually calculate which ones are stretches and all the other ones are going to be bends. In vibrational spectroscopy, all you can have are bends and stretches. You know, if you've heard maybe in organic chemistry, something like scissoring or a WAG or something like that, those are just, kind of silly names that are more specific versions of bends, I think it is. But really what it comes down to, right, a stretch is you're changing a bond length, okay? You're contracting and you're expanding a bond length. A bend, what are you doing? You're changing bond angles, okay? So that's all you can do. All you can do is change angles and change lengths. And, you can call things whatever you want, but fundamentally, that's all you can do, right? So what you're going to do here is figure out what the stretches are. And so because you're just changing the relative positions of the atoms along the bonds, what the symmetry, the representation of stretches is embodied by is just the symmetry of the stationary bonds. So all you have to do to figure out the stretches is come up with a reducible representation in the point group that you're working with of the stationary bonds. So we can call it gamma stationary bond, and we're going to label the bonds A, B, C, D, the four CH bonds in methane. And then we're going to look what happens, which one of these are stationary in the TD point group. And so for the identity operation, obviously all four, A, B, C, and D, don't move. They're stationary, so we put down a 4. In C3, one of them is going to change. I've chosen, one of them is going to stay stationary. I've chosen this CH bond here, right? And so bond A is going to stay the same because we're spinning through bond A, but B, C, and D are all going to interchange. The C2, remember, bisects these angles, these HCH angles. And so, atom H this H goes to this H goes to this H. So bond B and A switch places, bond D and C switch places. So none of them change. S4 is very similar, where it's the same axis there, and they also all are going to interchange. So you have 0 stationary. Remember, we're figuring out how many are stationary. And then sigma D, again, the easiest one to visualize here is the mirror plane that contains the A and B bonds, right? And so that's going to be right here. And so I can extend the mirror plane a little bit here. And you can see that, right, C and D, those are going to swap places, but bonds A and B are going to stay the same. So at 4, 1, 0, 0, 2, we're then going to reduce that. And how would you reduce that? Use the reducible representation formula, or this is actually simple enough. You can, look at this, 4, 1, 0, 0, 2. And so you can stare at the table for a little bit and say, hey, if I have 1A1 and a T2, that's going to get me 4, 1 plus 3, 1, 1 plus 0, 0, 1 plus -1, 0, 1 plus -1, and then 2, 1 plus 1. So that gave you 4, 1, 0, 0, 2. But anyway, however you want to solve it, you get out that your stationary bonds are A1 and T2. So what that tells you is that your A1 is a stretch and one of your T2s is a stretch. And indeed, that's what I showed you before. Anything else is going to be a bend. So what's left over? You have your E left over and you have another T2, right? And so those are your two sets of bending modes.